Hi there. So far in our unit on gradient functions and instantaneous rates of change and so on, we've been using it to try and find a specific um, value of the gradient at a specific point on the function. And what that function was didn't really matter. Now, in the previous unit's worth of work, we were looking at polynomial functions up to cubic, so quadratics, cubics, linear functions. And when it came to linear and quadratic functions, we were all okay. When it came to cubic functions, we were able to sketch them with one missing piece of information, and that is what is the coordinates of the turning point. So you can see we've got one here and one here. So given this function here, I know it looks a bit funny. That's because I was using it to illustrate a point. You could work out what the x-intercepts are. You could work out what the y-intercept is. You could use dominant term to work out whether the graph goes like this or whether it goes the other way around. But the turning point was something we left alone. Now, the method we're going to use to work out the turning point in this video could also be used for quadratics, could also be used, well, very trivially, it could be used for linear functions as well. But it also could be used for quartics, that means power of 4 functions, and so on. So it is a very versatile function, and it all comes back down to what exactly is happening for the gradient at the turning points. Let me turn on this, which is just a point that will trace. As I move A, it'll trace the point across the function like this. Okay, so this is the point at which we will find the instantaneous rate of change. Excuse me. So we've got the point A, comma F, comma A. Again, A is the input, so therefore F bracket A would be the F of A would be the output. So when A is input, F of A is output. And I've also got the gradient here as well, F dash of A, and you can see it's calculating it for us as 3.51. And I'm going to turn on this little line here. Don't worry about the structure of it, but I'll put this on. And what this means is that at that point there on the graph, it has a particular gradient, 3.51. So does this straight line. It has the same gradient. So we call that a tangent line. And next week we'll look at that in a little bit more detail. But I just wanted to give you that sort of context that we're looking at a straight line which has the same gradient. So as the gradient of the red function increases, so does the gradient of the tangent line because it's the same gradient. Okay, so you can see that both the green line and the red line have gradient 5.04. And I guess the point is that visually you can see that as I approach the turning point, the graph is getting flatter and flatter and flatter. You can see that it's now got a gradient of 0.31. That green line is quite flat until I hit the turning point like so. And you can see F dash of A is equal to 0. I've got a flat line here at the turning point. In other words, it is neither increasing nor decreasing. It is neither positive nor negative. It is 0 and constant at 0. Okay, at that point. And then away we go down the graph again. It's getting steeper, hits about the middle, and then starts flattening out again. It's like a roller coaster until it gets to the other next turning point, and it's flat again. F dash of A is equal to 0, i.e. At a turning point, the graph is neither increasing nor decreasing. It is 0, and then it takes off again. And if you want a lovely little roller coaster ride, you can do so. Yay! So you can see how the gradient is getting steeper and flatter until it gets zeros at the turning points as we go along there. Okay, that's all well and good. I just wanted to show you something else as well. If I take instead a basic cubic graph, which has been transformed. So if I go say, x minus 2, sorry about the capitals, x minus 2 or cubed plus 1, there we go. I'll just reorient that. So here's my graph here, and it's quite steep, as you can see. It's the points are off the line at the moment, and now it's coming up to being visual. Being visual, I don't even know what that means. So the point and the gradient is the same here. So the point is here. The gradient of the green line is the same as the instantaneous rate of change in the red line. And you can see it once again, it is getting flatter and flatter and flatter and flatter. And then the gradient is 0 at this point. this is, can you remember what it's called? It's called the point of inflection. So if you look at turning points or points of inflection, they all have a gradient of 0 at that point. And before and after, they tend to be fairly flat and then getting steeper or whatever else. Okay, so this is a really useful property. It means that whether we've got it in turning point form or not, or vertex form or whatever you want to call it, we can use derivatives in order to find these important points. Now, I'll just switch over to here. So we've got some little bits of theory here. And you'll note that I've called this stationary points rather than turning points, because really a point of inflection isn't a turning point, but they do have something in common, and that is they are where the gradient of the graph is neither increasing nor decreasing. So it's got a gradient of 0, and that is why they're kind of called stationary points. Notice the AR that means stationary, as in to be still. The graph is still at these points. So points of inflection or turning points. Okay. One thing we're not going to do in this video is we're not going to look at the nature or type of these, but just to flag it. So in other words, we're not going to be figuring out whether it's a maximum or a minimum or a point of inflection. We're just going to calculate what the stationary point is. So one phrase you'll come across is local maxima and minima, and the other one, which we're quite familiar with, is point of inflection. I'll just really quickly talk about local maxima and minima. So if I can just click on undo until I get back to that interesting looking function. Oh, would have been faster to type it in. There we go. We can see, I'll just zoom out a little bit as well. I'll just turn off this and this. So we can see that we've got a turning point here and a turning point here. And if this was a quadratic, we might call that a maximum and we might call that a minimum. But it's not actually a maximum or a minimum for this function, because although this is a turning point with a kind of a maximum here, and then it goes down again, when it goes up, it goes on forever. So there is no maximum. And similarly for this, even though this is a minimum just here, it's not an actual minimum for the whole function because it goes on forever. In fact, what you can do is you can take, say, a range like this. Oh, I'll make it to 3, say, for example, and zoom out a bit. So if I take the function like this, if I said over x between -4 and 3, i.e. from here all the way to here, what is the minimum for this function? The minimum would actually be down here, and the maximum will be up here. But these are still important points, because within the graph, it is a maximum it is a maximum value that it reaches before descending again, whereas this is a maximum that never changes, really. It's a maximum forever. And similarly here, it's a minimum that the graph reaches after decreasing before it starts increasing again. So they are still special, but because they're only local to this spot, we call them local maximum. This is a local maximum and this is a local minimum. Okay, so what we can do is we can do a little bit of mathematics in order to determine that a turning point that we calculate is a local maximum or minimum, whether it's a point of inflection, and we can even see whether it's a global maximum and minimum as well, which means over a particular interval of the function, is it actually the biggest possible value for that function? Okay, so let's finish this particular slide off. So stationary points are turning points and points of inflection. How do we find stationary points? Well, it's where f dash of x is equal to 0. Okay, so that's basically it. So I'm going to go through 3 examples, and that will do us for this video. It's already long enough, isn't it? But it's not too hard. So example 1, find the stationary points for this quadratic here. We know there's only going to be one, because we know what the shape is going to be. So the first thing I do is I find the derivative. So I go to y dx, and I simply use my power rule shortcut. So 2 times 2 is 4, x 2 minus 1 is 1, so it's 4x minus 8, and the plus 1 disappears. So dy by dx equals 4x minus 8 is the derivative, and now I set that equal to 0. One of the rare times I put an equal sign on the same line. I set it equal to 0 and solve for x. So I've got 4x is equal to 8, and x is equal to 2 by dividing both sides by 4, sorry. That's not quite the end of the story though, because that just gives us the x coordinate. So now I substitute in 2 for x in the function, not in the derivative, or the gradient function, but the original function, and I solve for y, like so. So I'm just substituting in. I'm now evaluating it, so that's 8 minus 16 plus 1. And 8 minus 16 is negative 8 plus 1 is negative 7. Therefore, there's a stationary point at 2, negative 7. That's also it's going to be a turning point. That's all we know it is. And we know enough about our nature to know that this is going to be a concave up graph, which means this is going to be a minimum. Just from our knowledge of graphs. Again, like I said, next week I will go through a bit more of a fancy way of doing it. Example 2 is x minus 1 times x plus 1 times x minus 2. Find the stationary points. So the first thing to do is find the derivative, except we can't find the derivative when it's in factored form because we don't have the tools for it yet. But if we look at the first two factors, we can see that's just a difference of 2 squares. So that's x squared minus 1 squared times x minus 2. And now I will expand that. You can use the box method or chicken bake it, whatever you want to do. So it's going to be x cubed minus 2x squared minus x plus 2. So that's basically it expanded. Now we can find the derivative, f dash of x is equal to 3x squared minus 4x minus 1. And now we can try and solve this by whatever method we want to work out what the value of x is when that f dash of x is equal to 0. Okay, so probably the best way to solve this would be to use maybe the quadratic formula, or maybe using if it's going to be able to be factorized, then perhaps we can use the method where we go 3 times negative 1 is negative 3, and our target is minus 4. And let's see if we can come up with that. So this tells me I need two numbers that are 4 apart that will add together to give me 4, to give me 3, sorry. And I don't think there are any numbers, so that doesn't factorize very well. So then we're going to use the quadratic formula, and we're going to go x is equal to negative b, so it's 4 plus or minus the square root of b squared, 16 minus 4ac, so that's going to be 12 all over 2a, which is 6. So that's 4 plus or minus the square root of 28 all over 6. Now I can evaluate that on my calculator. Now, just to make this video short, I'll leave it there and say that you can now use your calculator in order to evaluate that to decimal points if you want to, and then you can substitute them in to f of x to work out what y is. The third example we will see through, even though it is decimally as well. In this instance, we're asked to sketch a function showing all critical points. So notice it says all critical points, doesn't say everything but the turning point. So here we go. First thing I'll do is I'll expand f of x there. And although I've got a simple x times x minus 3 to do, these two things are again a dot. So I think it would make more sense to expand that first. So that would be x squared minus 9. And then I'll expand once more to get x cubed minus 9x as my function. Okay, so that's pretty straightforward so far. now we will find the derivative of that. So f dash of x is equal to 3x squared minus 9, and we'll set that equal to 0, and we'll solve it. So we've got 3x squared is equal to 9, x squared is equal to 3. And so x equals plus or minus the square root of 3, which means that that's roughly equal to plus or minus 1.7, roughly. So with those two values now added in, I can now work out what the y-intercepts, what the y-coordinates are. So I'll go f of root 3 or f of 1.7 is equal to, I'll probably just use this, 1.7 cubed minus 9 times 1.7, and that's equal to, and that's when I'll switch over to my calculator, and I've already got this sort of already prepared a little bit. So I will go the square root of 3, just using exact values when I can, to the power of 3. Don't really need those extra brackets, not what they're doing there. Minus 9 times the square root of x, or square root of 3. And that gets me an exact answer of minus 6 root 3, or approximate answer of minus 10.39. So you can use either the exact or the approximate one. I'll just put in the approximate one. Negative 10.4 is what I'll have there to one decimal place. So that's 1.7 and negative 10.4. And then we'll do the same thing but with negative root 3. And that'll be square root, negative square root 3 to the power of 3 minus 9 times negative square root of 3, which gives us positive 6 root 3, or approximately 10.4. So that's negative 1.7 cubed minus 9 times 1.7, which is equal to positive 10.4. So it's negative 1.7, 10.4. Okay, so we've now got our two turning points as well. So if I was actually doing this full sketch, I would go through my usual steps. I would be saying dominant term, first of all. Oh, sorry, I'll switch back to here. So we've got this, and we need to work out the dominant term. So the dominant term, remember, is working out what the x cubed, what's happening with x cubed. So x times x times x is x cubed. So x cubed is positive, which means that the graph, so negative, so when x is a negative value, x cubed will be negative, so it will start here and it will end here. So that gives us the direction of the graph. For the y-intercept, we let x equal to 0, and so we would have 0 times 0 minus 3 times 0 plus 3, so that'll be 0. So when x equals 0, y equals 0. Just to be mindful of that you don't accidentally go minus 3 times 3 is negative 9 and forget about that there. And then the x-intercepts are fortunately quite easy because it's already in intercept form. And so we have x equals 0, x equals 3, x equals minus 3. So x equals, so we've got 0, 0. We've got 3, 0, and we've got negative 3, 0. So there are x-intercepts, and our turning points are over the page, stationary points. Okay, so now we're able to draw the graph. and we can put in our critical points. So we're going to have a critical point here at 0, 0. We're going to have a critical point at 3, 0. So let's put that there. Oh, and that's negative 3, 0, sorry. And a point here which is 3, 0. There's our 3 critical points. We know we're starting here and finishing here in those quadrants. And we know the turning points are 1.7 and about negative 10.4 up and down. So let's call that about 10.4 and that about 1.7. So that's negative 1.7, 10.4, and then we're going to have another one about there, which is going to be 1.7, negative 10.4. Okay, so with our critical points in now, we can sort of have a crack at graphing it. It's a bit hard to do on the screen here, but I'll give it a go. So we're going to have something like this and this. Bit pointy, isn't it? But it gives a rough idea. And again, all the critical points are now included: the y-intercept, the x-intercepts, and the turning points.